Today I'll cover the chapter 5. Chapter 5 is beam. This week our drive, lateral torsional moment, capacity, and critical moment. Let's look at this one. It is a column that is very familiar to you. Column is subjected to axial force. So in this column we can calculate PCR, buckling load about the axial force. Today we have to consider this beam. The end moment increase, then the moment reach to MCR. Buckling moment. This is buckling load. This is buckling moment. What buckling? Beam buckling. Okay, beam buckling load. So we have to calculate MCR. Look at this one. Firstly, you have to consider the behavior of the beam buckling. I'd like to draw some figure. Let's consider rectangular plate. This end and this end is less strained against some rotation. Let's train like that. This end and this end. So in this end there is no lateral displacement and there is no rotation. And then the moment applied like that. MCR and MCR. If the moment is equal to MCR, this beam buckle. I'd like to show some buckle shape with blue color. Buckle like that. Can you imagine the shape like that? If you look at this section A, then we can draw like this. You see this drawing? So I have to remember this figure. This buckle like that. Then we have some lateral displacement, and then we have some rotational angle, lateral displacement and rotational angle. So in case of beam, the buckling equals lateral displacement and also equals some torsional angle. So we call it lateral torsional buckling. It is beam buckling. It is three-dimensional behavior. Along the member, we have to consider this direction. We have to consider this lateral direction also. And then we have deformation, as you see, vertical deformation. So it is a three-dimensional problem. So in fact, lateral torsional buckling behavior is relatively complicated rather than this column buckling. As you see, this column buckling, the shape is like that. X direction, Y direction. This is 2D problem. This beam is, it is called Z direction and Y direction. This is a side view. If you see the plan view, buckle like that. We have displacement U, Y, this Z. So beam buckling problem is basically 3D problem. So it makes the beam buckling problem complicated. By the way, if you see the section view, this is Y direction, this is X direction. You have lateral displacement U, this U. It is on the example of Y difference section. It has some vertical displacement. As you see here, moment applied, then we have the vertical displacement V. What else? This H is original position, and then after buckle, it moves like that. So we have the lateral displacement as well as this rotational angle, lambda. So U, V, lambda. You have three different displacement. As you see this in vertical direction, as moment increase, this will also increase. So it is a low diffraction problem in vertical direction. It is not bifurcation problem. And we have the horizontal, and then we have the angle. It is some bifurcation problem, buckling problem. It is a lateral torsional buckling at MCR. If the magnitude of moment reaches to MCR, the beam has lateral torsional buckling. So lateral torsional buckling occur in this beam. IX is greater than IY in this case. So when the beam buckle, it have the displacement toward this weak axis direction, y-axis. So weak axis direction, buckling occur. As you see here, V, vertical displacement is independent from U and gamma. So if U occur, this gamma must occur. So gamma component are coupled problem, but this vertical direction, V, is independent from U and gamma, okay? Because in this vertical direction is low diffraction problem that is independent from this lateral torsional buckling. So as I mentioned, it is 3D problem. This U and V is the bending deformation. This gamma is torsional angle. Torsional deformation. Because lambda is torsional behavior, so we have to look at torsion first. As you see this cantilever beam, this torsion or force applied. This sign means right hand rule. So torsional direction like this, corresponding to right hand rule. We have two arrows here. That means the torsional force, okay, not axial force. If we draw this one arrow, that means axial force. We have two arrow, that means torsional force. Direction is like that, based on right hand rule. Let's look at this one. This free end of this cantilever beam. As you see, axial strain is free. This axial strain, that is axial strain direction, right? It is free. There is no restraint. Original the section at this free end is plane, but after torsional force applied, this section is not plane anymore because this axial strain occur in right hand side here. So as you see, this part become longer, this part become short, long, short, like that. So that phenomenon called warping. That kind of warping free in right hand side. The section of right hand side is not plane. You have some longer part and short part, longer part, short part. It is called warping. So warping phenomenon occur at free end. At this free end, we have Saint Venant torsion only. TSV means Saint Venant torsion. Saint Venant torsion, the equation is this: Gj d gamma dz. Yeah, that is the equation. G is shear modulus. J is torsional inertia. J equal sigma 1 over 3 pt cube. You have the three plate 1, 2, 3. J can be calculated. This B times T cube, and this one also calculate. This one also calculate. Add together. That is the torsional inertia. And then this one is d gamma dz. It is gamma prime. I think you already learned this Saint Venant torsion in your undergraduate course. So Gj gamma prime like that. And if you see left hand side, it is a fixed. So that means axial strain fixed. There is no axial strain in left hand side. So this kind of warping displacement is restrained. In this section, we have warping torsion, TW, in this section. In fixed end section, we have warping torsional, the resistance. And this free end section, you have Saint Venant torsion resistance when you apply torsional moment. Then how about this middle span? You have Saint Venant torsion and warping torsion together. In left hand side fixed end, you have warping torsion, but not Saint Venant torsion. This free end, you have Saint Venant torsion, but not warping torsion. At this middle part, you have Saint Venant torsion and warping torsion resistance. That is the torsion. So you already learned about Saint Venant torsion in undergraduate, but this warping torsion, maybe you are first in warping torsion. So I'd like to explain some more in warping torsion. Next page. Warping torsion is this. If you see this wide flange section, we have H here. This is the plan view of wide flange section. As you see, the top flange deform like that. Bottom flange, it deforms like opposite, like that. That means top flange has some downward deformation. You can consider this shear force at top flange, this force. Bottom flange is opposite direction. You have the opposite direction, the force. You can consider these two force corresponding to this deformation. You can consider this MF, flange moment. It causes some deformation, this downward. Let's consider this moment, flange moment applied here. So MF equal this the EIF, bending stiffness. EIF times D square UF over DZ square. D square, this direction, and then DZ. UF is this one. This one is UF. You have some moment curvature relationship like that. MF equal EIF regarding flange. So MF equal EIF D square UF dz square. It results in EIF UF 2 prime. It is familiar, isn't it? At the column also you have the similar equation. So EIF UF 2 prime. That is the moment. If you consider this moment regarding this top flange. And then from this one you can calculate shear force. That is shear force direction at this top flange. Shear force equal minus DMF over DZ based on the equation. Then it results in minus EF UF 3 prime if we input this equation here. Okay, so the warping torsion can be calculated this coupled moment. This is top flange VF, bottom flange VF times H. So VF times H. So VF equal this one minus EIF UF 3 prime times H. So if you see this figure, you can consider UF here. That is UF, top flange deformation. UF, this is gamma angle. So you have the equation UF equal H over 2 gamma. Right? Because it is small deformation theory. When we calculate Buckner equation like that, so if you input this equation here, then you can finally minus EIF H square over 2 gamma 3 prime. TW, warping torsion, can be written minus ECW gamma 3 prime. CW called warping constant. Here IF is moment of inertia over one flange. 1 over 12 thickness TF BF cube. So that is warping torsion equation. So you have the previously Saint Venant torsion. That is Saint Venant torsion. That is warping torsion. So T equal T S SV plus T warping torsion. SV is this one. Warping torsion is that one. So that torsion equation can be written like that. Let's go through next page. Let's look at this. Because some distortional behavior is 3D looks somewhat complicated. So now I am explaining somewhat slowly. Let's calculate the MCR, critical moment, to cause a buckling of the beam. The shape is rectangular plate like that. In this both end, we have the restraint like that. That means we don't have any rotation at this both end. At this middle part, of course, we have some rotation. Firstly, you have to understand some coordinate system. As I mentioned before, this kind of column, coordinate system is simple because it is 2D problem, okay? X, Y. There is no rotation. It is simple. But as I mentioned, this torsional problem, that is 3D problem. If I draw again like that is beam. Let's consider the deformation due to lateral torsional buckling like that. It means it has a vertical deformation as well as lateral deformation. So laterally you have the deformation like that, and the vertically deformed like that. This lateral displacement called U. This vertical displacement is V. Firstly, you have to understand some 3D behavior. You have angle also. This gamma, torsional angle. This kind of some figure can be represent this free body diagram. Let's say if you cut this part, you can draw like this. So originally, you have some global coordinate X, Y, G, and then it deformed at this section. This part moved to here. You have displacement U, lateral displacement, and then you have the vertical displacement, right? And then you have gamma, torsional angle. Although you have global perpendicular coordinate X, Y, Z, if you consider this point, you have the local coordinate. X prime, Y prime, G prime. Because it is rotated, this is most Y prime. Okay, so vertical, some global coordinate, it twists a little bit. How much? Gamma, X. And then according to this Y prime, you have X prime. That angle must be 90 degrees. And then you have the Z axis at that local direction, Z prime. Z axis from this one like that, Z prime. At this point, that is local coordinate, X prime, Y prime, Z prime. If you consider this point, that local coordinate also a little be changed, right? Yeah, that is local coordinate. Firstly, you have to understand this coordinate system because it is 3D problem. We have to consider this local coordinate. as I mentioned before, just column, local coordinate, global coordinate is identical. Okay, this column, this x, y. After buckle, it is just same as this global coordinate. But here, this torsional problem, we have to consider this local coordinate system in order to calculate MCR, buckling moment. Here, as you see, we have the end moment M0 against x-axis, right? This M0 is against x-axis. M0 direction like that, if you consider right-hand rule, that M0 applied like this, two arrow in this direction. We have M external moment is MZ, right? How about, do you have any moment regarding MY, MZ? No, we don't have. Regarding global axis, then MY external, MZ external equal to 0. That is some global and local coordinate system. Using this one, I will derive buckling moment in the next. Okay, everybody, see you in next lecture.